So first, thanks a lot to the workshop organizers, Stefano, Marius, John, Lydia, Eng, for this kind of invitation. And before I jump into the topic, I just wanted to run a quick survey. Who's here more of a ML person versus systems and networking? So if you're more ML person, raise your hand. Okay, it's a mix. All right, so there's a parallel P4 workshop, and I got a sense that most of the programmable networks people are there. So I think for some people it might actually be news that you can combine programmable networks for distributed deep learning, and so that's the story for this keynote. And as this is keynote, I'm supposed to be dispensing some wise words and so on, but really I think I'm going to delegate today. And so let me just say congratulations to all of you. You made it to 2022. We now have models with billions, many billions, hundreds of billion parameters. Maybe we're already nearing trillions, right? With fantastic set of applications and so on. And I'm glad you didn't mention any of this in your opening remarks. Okay, this is just some examples that I picked up from Twitter. As you know, over the past week, ChatGPT was all rage. Everyone here understands bubble sorts, but you can get bubble sort explained in the style of a fast-talking wise guy from the 1940s gangsters movie, and actually it makes sense and it makes you laugh. It can remodel your your living room, if you will. Okay, this is fantastic, right? This is all great innovation. So how did we get here, right? So the one thing that Mario was hinting at is essentially this perfect storm that there has been, right? Like many before, I'll just keep on repeating. We have come to realize and install a virtual cycle in which for machine learning to really boost its success, we have increasingly sophisticated models that take advantage of increasingly larger data sets. And for as long as this trend can continue, all these massive advancements and kind of like magical results are going to keep happening. But what happened underneath, right, was the innovation that basically happened at the infrastructure level, both at the hardware as well as the software systems, making ubiquitous, particularly parallel programming available to the masses, to the machine learning developers. And this happens to be in the form of clusters with hundreds of machines, if you are referring to data centers and clouds. And each of these has hardware accelerators. Maybe that is GPUs most commonly, or TPUs, or some other ASICs that are coming up. And yet, despite all that leap in very costly infrastructure, the compute requirements for AI, for these very large models, are keep on growing and growing. And so I think this is actually a little bit of an old quote, but people observe the doubling happening every 3 months, right? Unparalleled type of an exponential, and not comparable to Moore's law. So the implication of that is training models is still very time consuming, and it could take days or weeks, and it's very costly, and it's also not just in terms of monetary, but for energy. So today I want to tell you a little bit about the work that we're doing in that space, and then lead up to some of my own thoughts about the future for this area. So I'll start with drawing something which I characterize as distributed learning workloads, to give you more or less a fuller picture of what happens when you train large models. So of course you have training clusters with these GPUs and so on, but the picture really would not be complete if you omit the presence of data and the presence of what needs to happen in the middle in terms of filling the impedance mismatch as you go from raw data into something that actually represents a sample that the GPU would understand. I'm not going to focus a lot on that because I know Anna is most likely going to address this part very well in her keynote, but I will touch a little bit about this box in the middle. So, of course, deep learning is primarily a compute-intensive workload, right? That's why we have all these needs for GPUs. But I think we need to really be mindful of the scale at which we're talking about, and also the trends that are supporting that scaling. And what I mean by that is essentially the fact that within deep learning, yes, there's a lot of computation, but there's also a lot of data transfers that is happening. And therefore, the role of the network is non-trivial. So let me start with a primary focus on the data parallel style for deep learning by focusing on what happens within a training cluster. So most people probably by now have heard about data parallel distributed training, which is the idea that you have a replica of the model in every worker, in every GPU. You partition the data that you're training on, potentially scaling and enlarging your mini batch size. And then you run stochastic gradient computation to do stochastic gradient descent to compute the gradients. And then you have this problem, which is you need to synchronize the gradients. And that leads to an all-to-all intensive communication pattern at the end of every iteration of SGD, doing which you're trying to aggregate those gradients to get the estimate, actually, of the gradient that you want to move based on your step size or learning rate. The issue at scale is that that data could consist of hundreds of megabytes, if not gigabytes, and you're going to have to do it at every iteration. So that quickly becomes very network intensive. Traditionally, the solution to solving this aggregation problem were parameter server, primarily, I would say, discussed and brought forward by the machine learning community, where the architecture was fairly simple. You have more or less a centralized component, at least logically centralized, where all the gradients were pushed by the workers. They would get aggregated. You would actually keep the replica of the model at parameter server, and you would run the optimizer, computing a new version of the model parameters, and then before the next iteration of SGD, all the workers will pull the updated parameters. However, it turns out that this could easily become a bottleneck, especially if there are several resources that you didn't have or you didn't dedicate for this were not commensurate to the need for communication. So another trend was instead turning the page on that and borrowing from the HPC community collective communications, particularly in the form of something called O-reduce, where you run decentralized communication with one across many algorithms. Here I'm showing the most famously employed ring O-reduce, where you set up a logical topology, a ring in this case, across all the workers, and then you communicate peer-to-peer, and you share that gradient information while you aggregate it. So I'm going to zoom in, however, a little bit more, because what I showed you before is just a high-level communication pattern. So I want to zoom in and show you a little bit more about what is happening in terms of communication. So to begin with, people who build PyTorch, TensorFlow, and so on are very serious, software engineers, and they are aware that to the extent that network could become the bottleneck, it should be alleviated. And so if we actually consider the layer-by-layer structure of your neural network, what is happening is that as you start to go forward, as you start to go backward in your back propagation, the gradients of the layers become partially available. And so you use that incrementality of that computation to already start the gradient synchronization. So let me illustrate this with an example. We have forward pass, loss function, and then we start to compute the gradients, right? So as soon as I have the gradients for layer 3, I can start communicating. And of course, this is good because I can overlap at this point the computation of the gradients for the layer 2 in this case with the communication for the readily available gradients for layer 3. And I can keep on doing this. And so now you kind of like must be guessing, okay, what is the network bottleneck? What is the problem, right? So if you can do this overlap properly, all of the latency of the communication might be masked. Well, the issue is that if there is a lot of communication volume that needs to get across, then indeed you may be needing to wait on the network. And that is when the network really becomes a bottleneck. And so now, let's come to grasp with reality. So I'm showing here two relevant trends in the space, portraying at which rate general improvements in terms of compute for AI and machine learning, say GPUs, are progressing versus networks. This comes from NVIDIA themselves. So over 4 generations of GPUs going from 2016 to 2022, thanks to Moore's law, they were able to scale by 8x plus, all the additional, improvements in terms of full stack innovation and probably cross-layer optimizations. They actually brought a massive amount of improvement, right? 26x. So keep that, figure in mind as you instead look to the right. The right is the most recent report on data center Ethernet, and given converged Ethernet trends, Ethernet is the more relevant technology to be talking about. And what it shows is on the y-axis the volume in millions of number of ports being deployed, and the color of this bar, the color shading, represents different Ethernet speeds. And so you can see at a glance that yes, there is also a doubling, right, in terms of network speeds, but the actual deployment is falling behind, right? It's stagnating. It's not as fast, and it cannot keep the pace in the face of a 26 performance improvement in 6 years. So based on that, I would like to suggest that network is indeed a bottleneck. Communication is a bottleneck for distributed deep learning. And that if you were used to think of it in terms of a simplification, which is just consider the ratio of communication to computation, we have to be a little bit more accurate and really think that the more accurate understanding of the bottleneck is to consider the non-overlapped communication. So this is actually a real training of one particularly large model, a 2.5 gigabyte model called DeepLight that does the recommendation. This is how long it takes to compute the gradients in V100, 87 milliseconds. And this is how much it takes to send all of that gradient data. And for as long as you have all this communication and you cannot overlap it with computation, then that is the exposed or non-overlapped communication that really becomes a bottleneck to scalability. And this is not just the case of DeepLight. We have run measurements in our group, and we've seen essentially that even scaling the network speed, the previous results were for 10 gigabit per second, but going even on 100 gigabit per second, there remains a significant share of communication that is not overlapped, that it makes part of a significant percentage of the iteration time. And so for as long as that remains the case, then data parallel deep learning, which is the most straightforward and the most desirable form of parallelization, really cannot keep on scaling. So I'll then tell you about what we are doing about this problem, okay? And from now onwards, I would suggest that if you have any questions, just shoot right away. There's no need to take everything at the end. But I hope the premise and the background is so far clear. So in-network aggregation is what we have been proposing for the past several years. It basically stems from this observation that at the infrastructure level, we have a setup that may look something like this, especially in rack scale systems, where all of the data is basically traversing the switch either to reach a parameter server or to perform or reduce. And this network is, in a sense, dumb and is not doing anything. So we were asking, is there something that the network itself could do to help with gradient synchronization? And so it turns out, and maybe later you want to step inside the P4 workshop to fill up a lot of that knowledge. But it turns out that a recent trend in networking has been towards programmability of the data planes. So there are now switch chips that are deeply programmable at the data plane level, meaning that you can write code that processes packets at line rate. And when I say line rate, we're talking about in this generation, which was the first model, 100 gigabit, but today you can buy a second and soon enough third generation versions of this Tofino chip, and you can do 400 gigabit light rate processing, for example. So based on that trend, we built something that we call SwitchML, where we co-design together distributed machine learning with the networking support that it needs in order to scale better and lower the latency for gradient aggregation. What is non-trivial about doing this is that this kind of programmable data planes are not general purpose are hardware targets, of course. You only have limited amount of computation, limited amount of storage. You cannot store an entire model in a switch chip. You actually have few hundreds of kilobytes of memory. There's no floating points, which is the backbone for SGD to run. And obviously, this is a networking design, so inevitably you have to deal with packet loss. So I will not have time to really go into the details, but we have paper and an SDI. We have an open source implementation, and we also have a full-fledged tutorial on this. So let me pick kind of like the salient highlights for this co-design. So to begin with, the philosophy is to try to carefully balance the load between the switch and the host so that we cope with limited computation and limited storage. To address the need for the lack of floating points, we have to run with the quantized integer operation, which we're fortunate enough because machine learning, deep learning turns out to be stochastically robust enough. And then we design our own failure recovery protocol, as well as an in-switch RDMA implementation to reach the highest possible level of performance. And that allows us, as the main result, to be 2 times faster in theory than ring or reduce. And in practice, we demonstrate sufficient benefits over NVIDIA nickel, as well as better scalability.
Sorry?
Yes? Can we close the door so I cannot hear?
I understand that you can handle the floating points. How do you account for loss of performance as a result of quantization?
We do not observe loss of performance, and I will also have a key result to show you, but empirically we do not. Okay.
What is
Yeah.
NCCL again?
NVIDIA collective library. Yeah. Okay, so let me show you the main insight about how to do aggregation in the switch. Which is essentially a streaming aggregation protocol, as we call it. And I'll simplify the setup. Just consider 2 workers. Let's say that these blocks that are shaded in red and blue are the gradients, and we chunk them into blocks. Let's say a block could be 256 floating point values that we then quantize. We regard the switch as a pool of aggregation slots. Each slot here is capable of aggregating 256 values at once. And then we use a deterministic way of mapping blocks of those gradients into the slots at the switch. And we can essentially stream this information. The switch aggregates them by doing integer additions. And then once the switch notices that all the workers have contributed, it can send back that block to both workers in this case. As this block arrives, that implicitly serves as a flow control signal to say, well, now there's a slot that has become empty and it's available. So we're coupling this transmission between workers to occur at line rate according to whatever the available bandwidth that connects them to the switch is, essentially as fast as possible. And we're not really worried about this tightly coupled communication because we understand that this is essentially doing bulk synchronous processing. So the gradient aggregation acts as a barrier, and you want to go as fast as possible within the limit of how the workers are progressing. So this is I will argue, an elegant solution to solving this problem. But as I said, we have to basically work with integer quantization. So that quantization, we make it happen on CPU cores, or we offload it to the GPU or bait as a small performance penalty at the worker side. And we also implement failure recovery, which is essentially packet retransmissions at the worker side as well, so that we can keep all of the switch resources essentially for performing switch fixed point aggregation at the switch. With regard to your question, this is the type of quantization that we're doing. We're basically trying to convert, let's say, 32-bit floating points into 32-bit integers, and we are conscious of the fact that this could actually have a fairly substantial quantization error. However, we leverage the fact that the gradients are grouped into blocks, and we perform a scaling before doing the conversion from floating points into integers. Specifically, we determine some scaling factor that is given to us by finding out across all the workers what would be that scaling factor that maximizes the dynamic range for those 32-bit integers. And once we have figured it out, then we do the rounding of the gradient values for that block multiplied by the scaling factor, and then later we recover it. In order to know what the appropriate scaling factor is, it means that we kind of like need to run a look-ahead procedure that piggybacks on the fact that we're going to send some other data. So we basically, before I send the block, I'm going to aggregate over the network and find the maximum scaling factor that I need to use. And by the time that information is available, I can then perform the quantization. And this is one example of the empirical evidence that we have collected that we can, in practice, doing this kind of quantization, train a neural network in a similar number of iterations as an unquantized one without implications on the accuracy. There are, in the papers, there is 8 different models, and we report this kind of plots for each of them. Yes, the scaling factor is across, and that is why we first have to run this agreement type of computation, which is taken care of by the switch. By the way, the switch does the same kind of reduction, but in this case, we're computing a max instead of a summation. It's essentially, yes, it's essentially a moving window. Now, the good thing is that, because we're hooking up workers directly into the switch, and the switch is giving us very good aggregation performance, not surprisingly, SwitchML can be faster than something like Ringo reduce. Here's some results. On the left-hand side, we have a setup with the actual P100 GPUs that we had in our testbed and a 100 gigabit network. And we're plotting the speed up relative to doing nickel or reduce with RDMA. And you can see that the speed up varies across different models. There are models that are more communication bottleneck, and therefore they enjoy a higher speed ups. And there are models wherein there may not be necessarily the larger bottleneck, and so the speed up is more modest. However, this kind of setup had essentially P100 GPUs, now 4 generation olds, and 100 gigabit network, which is not really representative. So at that time, we ran an experiment in which we artificially accelerated the GPUs by 10x to see what, in a more realistic conditions, our system could deliver. And so that is the plot on the right, which is also portraying the speed up over nickel. And you can see that now the amount of speed up tends to over around 2x for most of the models. Say it again.
The baseline is quantized model.
The relative, so the speed up is over doing nickel or reduce. So this is a throughput measurement. So this is how fast basically you're training. In terms of accuracy, we did not see essentially any significant drop. I say no, it's not quantized, the baseline. Yeah. The other property of SwitchML, which is actually something that makes it even more interesting as compared to nickel, is that its performance does not depend on the number of workers. So this is the issue with all these kind of overreduced algorithms, which create a logical topology, a peer-to-peer communication. they end up having a number of steps that has a dependency on the number of workers. So as you scale and increase the number of workers, you can see the performance for nickel here in orange that starts to decrease. This does not happen with SwitchML, and it will not happen for as long as you have available ports and available capacity on the switch, since every worker can stream data directly at the line rate that it supports. Moreover, we have done an excessively, perhaps excessive amount of engineering here, but we were really careful in tuning the system performance and making it reach as close as possible to the max RDMA goodput of the network. So that is also further improvements over nickel. Now, in terms of this somewhat annoying part, which is the quantization, most recently this year, we had another paper in which we considered what would it take to actually perform floating point operations directly on programmable switches. The short answer is that you cannot do it because some primitives are not available in the instruction set of these programmable switches. So we proposed certain mechanisms that could enable native floating point support in these commodity pizza switches, like the Tofino switches, should the hardware manufacturer decide to integrate. These are very simple things, like doing, instead of shift by 1, doing a shift by an arbitrary number of bits, and a few more things. And if we could do that, obviously we're going to start to work directly with floating points operations without loss of precision. It would also free up resources in terms of those CPU cycles that we're otherwise now using for the quantization, transforming from floating points into integers. So all in all, we're hopeful that something like this could happen in the soon enough timeframe with new releases. So I'd like to recap. So in-network aggregation is a solution that we have proposed to address the network bottleneck of distributed data parallel deep learning. SwitchML performs data aggregation along the network paths using programmable network switches. And the benefits of doing this kind of offloading of the aggregation to the switches is to, of course, improve the end-to-end training throughput of deep learning, be able to perform aggregation at, let's say, sub-RTT latency and independent of the number of workers, and also, as a side effect, reducing the total amount of traffic on the network fabric, which means that there is now more bandwidth available for other things. Right. So now we didn't actually stop there. We created what some may call the world's fastest or reduce drop-in replacement. However, what we notice is that for a substantially large amount of the models that we were playing with, the gradients are in many cases sparse, and this is primarily due to having very large embedding layers in those kind of models that result in basically a lot of zero elements in the gradients. So why would you want to send 0 over the network? So we basically went back to the whiteboard and started asking, can we take advantage of the knowledge that these gradients are highly sparse and figure out how to efficiently aggregate them with a similar style of aggregation, let's say something heavily inspired by in-network aggregation. And so in order to do this, we tweaked a little bit the design, I would say, of our streaming aggregation protocol, and we created OmniReduce, which does sparse streaming aggregation. When I say we tweaked it a little bit, it's because essentially we wanted to adopt this block-based notion for dealing with sparse data, because the most conventional solution is instead to use index and value pairs, whereas, however, you have the overhead of the index information as a metadata, which can be costly. So what we do is we have a little bit of metadata, something that identifies the next non-zero block, and we still preserve this block structure for all of the gradients. So every worker will split data into blocks, and the goal is to stream only the non-zero blocks to some kind of aggregator component. Now, the aggregator, you can think about it as the switch. However, when we started the work, we were not sure we could implement this higher complexity onto the switch. So we worked, at a more algorithmic level. We worked purely with software, and then once everything was said and done, we were able to see that there is a version of this that could actually run on the switch, and some other side effects that I will mention in a moment. So the idea is that every block carries this metadata. What is the next non-zero block for every worker? And the aggregator has an algorithm through which it maintains the global next non-zero block across all the workers. And this, through this and piggyback information, we can essentially ask every worker to send us the correct set of blocks. Now, this is one single thread of computation. Of course, in order to make this work, we have to perform several of these threads through fine-grained parallelization and saturate the bandwidth. But once we do this, then the result is that we can further improve the performance as compared to SwitchML. In this case, I will remark this is a software-based implementation of SwitchML for fair comparison. And this is, again, a relative speed-up plot of the training throughput, where you can see that OmniReduce can deliver 2.23x faster training throughput as compared to SwitchML on a 100 gigabit network. We also compare with what is readily available, if you will, in PyTorch, which is something they call the AG sparse, which is a all-gather-based sparse or reduced collective that is just, not nearly as performant even as SwitchML. Yes.
Can you compare about the other algorithms of them, like else before or something? They also exploit sparsity.
Yeah, we didn't compare with that kind of compressors, but we did compare against SparkML and Parallax, which are recent proposals that were exactly trying to address the same problem statement as ours. And in all cases, the performance was just superior. A side benefits of actually having worked with software, purely software in this project, was that the solution was, readily available. And so we didn't have to convince anyone to deploy a programmable switch in the production. And so thanks to that, there is actually a company in China, Meituan, that adopted OmniReduce, and they use it for some of their workloads that involve recommendation model with high sparsity of the gradients. So a lesson learned here was, doing things also in software actually helps. Yes.
If so, I guess that right now we're talking about non-general kind of things. So if you are developing there and begin multiple work, and how it can be repeated.
So, yeah. So I think the question is, and I think we got the worst possible room here. But if I got the question correctly, the question is, what kind of hardware are we talking about here? So we are basically in a data center scenario, and how we can reconfigure it. We're considering a data center scenario. We are primarily focusing on a rack scale version. We're working on hierarchical SwitchML, where you could traverse multiple switches, but to begin with, we needed to solve the problem with just one switch. And so the idea is that this switch is, there are multiple vendors that would offer you, but at the core, you have something like Intel Tofino chips. That's, what we have been able to do. Some other people have been able to perform in-network aggregation with a Jupyter switch, and since they bought Mellanox, they have something called NVIDIA Sharp, which is customized switch chip, where they also can do in-network aggregation, although that one remains a proprietary solution. With respect to the reconfiguration, that is not really the assumption that we have. We take here that if this is the workload that you have, typically you would design your training cluster, provision enough bandwidth, and you happen to know that this is an important primitive that you would want to offload into the network. We were able to do it both with SwitchML, and then ultimately, as I mentioned, even though we worked with software, we back ported, if you will, omni-reduced logic to also work inside the switch, and we were able to demonstrate that it works. Yes.
I think I'm still trying to understand.
Yeah.
So where's the benefit? If it's one thing I understand is your cost and line rates and application faster, less hops to click and
Yep.
stack. You also say you reduce traffic on the network. Trying to understand if there's still the same volume of stuff being communicated.
Okay,
so
so relative to a ring or reduce, you have a factor of 2 reduction in terms of volume, because in ring or reduce you have to traverse the ring one time, let's say n steps to share your stuff, and then you need to gather. So you need to go again in the ring n times. So your volume, if let's say D is the volume of your gradients, total volume ends up being 2D. In this case, it doesn't happen. And you know,
one sentence, more like
yeah.
a parameter server thing.
Yes, it's a streaming. Yes, you could think of it in a software word. You can think about it as a streaming parameter server. Yeah. Sorry. So the main scalability issue that this solution has is if you run out of the capacity on the switch. So if you finish that capacity, then you have a problem. So right now we're working on a hierarchical version where you can think about it. You can distribute this. You can have multiple of these instances of the system, and you have different layers of your aggregation, where at every layer of aggregation you have an n-to-1 reduction in terms of volume, right? Where let's say, well, n is probably the wrong number now, because n could be the total number of workers, but let's say if m is the number of workers inside one switch, then you go m-to-1. And then you can collectively take another m switches, and you can go into one single switch. So it is a good model, right? Because it allows you to recursively reduce the data volume of your traffic. But we haven't finished this work, so I'm not. Yes, this is a rack scale version of this. Yeah. So I'll now move on, and I'll tell you about however, doing this kind of in-network aggregation, not with switches, but on a SmartNIC, right? So the latest trend, and Mario was mentioning, is something where you can have, more intelligence inside NICs. Omni-reduce requires these extra server machines, or you would require extra programmable switches. And as I just told you, the company that adopted the technology was not happy to deploy that. Plus, we have, even in the case of omni-reduce, we have high CPU utilization for I/O. And the reason is, despite we work with RDMA, we need to have enough fine-grained control of all the I/O to include the metadata. So the idea is, if you could offload gradient aggregation to the SmartNICs, then you could save CPU cores, you could improve further on scalability, and you would not require the extra servers or the extra switches. So it seems like a tempting idea, and so we started creating a port of the omni-reduce algorithm to what I would say is the best-in-class SmartNIC today. It's actually not even called a SmartNIC anymore. It's called the data processing unit. This is the Bluefield 2, which is a collection of general-purpose cores, in this case, 8 ARM cores that are attached to the chip, the NIC chip, in this case, the ConnectX-6. And then you have some amount of RAM and the sheer bandwidth that is available. So we had to do some re-engineering. Okay, this is probably not very scientific, but there were actually some interesting challenges there as well for the threading model and the memory allocation to best match the capabilities of the NIC. However, what we found out so far is that there is, this provides insufficient performance as of today and scalability. There is this plot that you see here is a a workload in which you are trying to do a reduction of 800 megabytes of gradients, in this case, floating points. This is one advantage of the SmartNIC, is that you could work with floating points. And the Bluefield 2 performance is in green, whereas if you do it on a 5-year-old x86 machine, is the bar in blue. And the y-axis is latency, so lower is better. And we have two settings. One is sparsity 0%, so we aggregate all of the 800 megabytes, or very high sparsity, 96%. And you can see that there's inferior performance clearly. It turns out that there are at least two main problems with what we're trying to do. First, the memory bandwidth that is available in the DPU is too low to support 100 gigabit aggregation. Second, we have some issues with our control logic, which is inherently not scalable because it's scaled quadratically with a number of workers. So as in this case, we used 8 workers, but as we increase the number of workers, that control logic also takes a toll on performance. So right now, this is still part of ongoing work, and we're pursuing some different algorithm designs. There's nothing too concrete, so I'll not spend too much time. But I think that this is overall an interesting direction in terms of bringing a different spin of in-network aggregation in a way that probably can take more of a foothold also in terms of deployment. So now let me turn page and say, okay, so you could do that with in-network aggregation. You could do in-network aggregation also with highly sparse data. What about gradient compression? So the idea of gradient compression is you could tackle the network bottleneck by doing lossy compression to reduce the data volume. There are many techniques that have been proposed in the literature. You can do quantization. You could do sparsification, where you sample only a few elements of the gradients and you don't send everything. You could do lower rank decompositions, in which you view the gradients as a matrix, and then you decompose it into 2 matrices that are smaller to recreate the gradients. This is actually a really interesting idea, because it really combines more of an algorithm spin in machine learning, but enough let's say awareness of systems. And it raises an interesting trade-off, because inherently, due to the fact that compression is lossy, you kind of like start to play on accuracy versus training throughput. But as a systems person, I would further say that you have to also be very mindful of what the compression efficiency is like, the compression as well. So why do I say that, algorithmically this is interesting? It's because despite compression being lossy, people with a math background have been able to prove theoretical convergence guarantees. That is, even though you don't send all the information and you have an error, you can still prove that in many cases, training with compression will converge using the same asymptotic rate as with SGD. Oopsie. However, there's actually in practice implications that we observe empirically, as well as others, particular with regard to this accuracy versus training throughput trade-off. If you think about it, smaller data volume means faster communication and means faster iteration time. But lossy compression, what it does is that introduces statistical variance. That is, your estimate of the gradient is noisy. It's no longer the one that you would have wanted. And so the implication for that is you may actually have more iterations to complete in order to reach convergence. And so the real speed up is something that occurs if, when you do compression, right, T times I is less than the T times I when you were not doing compression, obviously. Well, how does that really apply to the real world? It turns out that people, kept on publishing compression here, compression there, picking, if you will, a little bit cherry picking, workloads and comparisons and so on. So in a recent paper, we built a framework, we call it GRACE, and we implemented 16 compressors from the literature, picking the most popular ones. And then we compared them across several different scenarios, several different benchmarks, different domains. And here's one particular one, which is neural collaborative filtering with 8 workers. all the results that I'm showing here are relative to the case of not doing compression. So when you see a 1 on the y-axis, that means this is what you would get without compression. And the left plot shows relative throughput. So if you have a speed up, you will be higher than 1. Whereas the right plot shows the data volume that you're sending. So sending less than what you would have sent originally puts you on the left of the 1 on the x-axis. And on the y-axis, you essentially have the model quality metric. In this case, it's called best hit rate. So the higher is better. There's a lot of information here. Of course, I don't really have the time to go into all the details, but I'll just basically highlight a couple of takeaways. One is compression is really not always a win. Anytime that you are below a 1 on relative throughput, it means that you are actually slower. And this is happening in quite a number of cases. And the second one is that the volume and quality not always correlate. So despite what intuitively one may think, which is the less volume I send, then probably the more error I have. And so they have less convergence, less quality of the model. This is not always true. It's true in some cases, but not always. But the bottom line, really, conclusion was that there is no one size fits all, and the compression has overheads, essentially, that cannot be dismissed. So with that in mind, we have done some work. I don't really have the time to cover everything, but we have worked in the space with quantization approaches, where we have an approach called natural compression, where we are trying to round stochastically to the nearest power of 2 for every gradient coordinate. And the reason that you want to do that is that once you represent your numbers in the standard IEEE floating point, and you are rounded to a power of 2, then you can drop the mantissa. You can just send the exponent with the sign, and you can make this compatible with in-network aggregation. In terms of sparsification, we worked with threshold sparsification, where the idea is you send every coordinate from the gradient vector that is in magnitude above a certain threshold. And the reason is that one has very low overhead. It's O of n asymptotic, but actually, if you parallelize it on a GPU, it's really fast. But the issue is that nobody is going to really give you the threshold. It's very hard to find. So the core contribution of that work is how to find appropriately, how to estimate it appropriately. And then we also consider something that is not quite typically looked at in the literature, which is if you're doing compression in dynamic networks, let's say in cloud computing, where the bandwidth that is available varies all the time, you really want to make your compression adaptive and change as the condition change. So we had some work that we called DC2 published at Infocom on that. In all cases, we were able to demonstrate fairly substantial gains over the no compression baseline. So let me recap here. There's a network bottleneck in training, and I presented to you in-network aggregation, in which the primary design that we have is switch ML to optimize communication infrastructure, customize the network to support aggregation directly. We then looked at what happens if your data is sparse, and so we produce OmniReduce to do efficient streaming aggregation inspired by in-network aggregation, but with sparse data. And then I also reviewed a little bit about the work we have done in terms of gradient compression. And what I will note is that in general, this last thing involves a bit of a trade-off between training throughput and accuracy. So it's less common to actually find it applied in practice. Yes?
So can we use the combination of the second and third, or the sort of?
That's a very good question. So I didn't have time to answer that, but the answer is yes. So in fact, in some cases, what we had noticed was the sparsity of the gradients was not really good. And so when the sparsity of gradients is not really good, OmniReduce performance reduces to essentially doing switch ML. So what if you actually perform gradient sparsification on top of doing that sparse collective communication? So in that case, it doesn't really work well because you sparsified gradient elements. So what we created is block-based gradient sparsification, where you sparsify blocks. which is more or less a trivial extension from the general theory of delta compressors in the specification literature. We just applied it, and so we have ability to do top K block specification, random K block specification, and we did we give convergence guarantees. And with that, we were able to provide improvements. But we also did observe that essentially at that point you have a trade-off between your accuracy and your training throughput. But thanks for the question. That is.
Another question.
Yeah.
Is about the penalty of overhead related to compression decompression. How does that play in to this? So do you have a latency impact, or what's the cost of doing the compression?
So you're not referring to Omni reduce anymore, right? Or you're referring to the combination that I told you?
Not the Omni reduce.
Okay.
Just the gradient.
Yes. So for gradient compression in general, you have a cost. In part, you can try to reduce it with careful implementation, careful engineering. So some of the stuff that we've done was to partition. So for example, if you do threshold specification, it's a very simple operation that is easily parallelized on the GPU, right? But I needed to have an estimator. And so then I needed to run the estimator and decouple it from the main training. However, at large, I would say it still remains an open question how to really systematically minimize or avoid the overheads of compression and decompression. And if you do not avoid them, then you are in this situation where, depending on the model that you're training, you with the same compressor, you might be on this side of the bar. Okay.
In general,
Yeah.
sorry. In general, is there a latency constraint that you have, or is it purely best effort?
Well, I think that in some workloads, you might actually have a budget, like a tight budget. The model needs to be trained by this time tomorrow, and then you have could be, but some models could might need to be fine-tuned, and so you have maybe 1 hour. So if we have that information, then you could actually then use it to tune how aggressive you are. I haven't really seen a lot of work in that direction, but that there has been a few work that consider a deadline, specifying a deadline. The closest thing that we have done was in this DC2 work was to account for the fact that the network bandwidth itself might change, and so at that point you may want to adapt compression. But let me say, adaptive compression is still not something that is widely explored as much as it could be. All right, so we're kind of like running out of time. So let me just give you very quickly a glimpse of what we're doing with regard to this part of the workload. So remember, I told you we have raw data, and then we have our training cluster on the right. And then in the middle, there is this kind of ELT transformations, as they call, where you are taking raw data and spitting out training samples, put in simple words. This is actually becoming a fairly elaborate area of research, also motivated by some real-world observation. This is a recent paper from people working at Facebook, in which they noticed that the bandwidth that is used for ingestion of data has just been growing at an unsustainable rate. And secondly, also the amount of power that they're using for some of the workload, not in all cases, but for some of the workloads in this pre-processing stage, so-called, actually turns out to be much higher than anticipated, and possibly higher than the training as well, the amount of energy spent for training. So what is the issue with pre-processing? It boils down to, in essence, finance. You have GPUs. That is probably the most expensive component in your cluster. You want to avoid data stores. You don't want to have GPUs that run idle. And so how do they solve it in Meta? They basically say, where we might have to allocate between 9 to 55 CPUs per GPU worker, right, to actually keep it busy, which is then, of course, very expensive and not super energy efficient. It turns out that a lot of the transformations, however, are very simple operations. So we have started working on adapting some of the lessons we learned from doing in-network computing and mapping those kind of transformations into a P4 switch. You can't address everything because some of these things are just too complex. But for the simple ones, we were able to express them as network functions that execute on a Tofino 2 switch. And we only have very preliminary results, but we were able to observe that with some random workload in this case, because the workloads are completely missing. That is something that I can go on and rant a little bit about later. But in some random but pseudo-realistic conditions, we were able to observe that if we are able to perform the pre-processing on the Intel Tofino 2 switch, we would be 65 times more efficient in terms of energy consumption, or gigabit per second per watt, to be more precise, than doing the same type of pre-processing operation in a highly optimized version of those data pre-processing operations done through fast-click in an Intel servers. Anyway, I think that Anna is going to really spend a lot of time on this, so maybe we can back to this later in the panel as well. So I want to give you some main takeaways from this. Deep learning requires plus compute, plus data, plus parameters. The more you throw at it, the better it gets. And distributed deep learning is a must to train large models. There are indeed many forms of parallelisms and more that are coming out that are being exploited. And typically they need to be combined. Today I only talked about data parallelism, but of course there is model pipeline and more advanced forms of decomposing the computational graphs to really reap the advantages of parallelization. In all of that, still network communication often becomes the performance or the scaling bottleneck, and I presented to you 3 solutions in network aggregation, faster collectives with sparse data, and gradient compressions. I also quickly zoom through the type of work that we're doing to also lower the bandwidth requirement and the energy and make it more energy efficient to perform data ingestion. But if there is a higher point, is that as I guess as Mario actually really better put it, is that there is this intersection between machine learning and distributed systems, which is a fun and impactful research area. So maybe more people from P4 workshop should have come here today. So let me conclude with some musings or ramblings that can actually characterize a little bit more how you might go and approach this area. So first, we actually seen this plot already, the one on the left. Number of flops that it takes to train the models has been exploding, and essentially, distributed deep learning is not going to go away, not going to go anywhere. But the one that I want to maybe stress now is the plot on the right, which is the memory wall, right? The one that essentially requires for the large model to really be distributed with many forms of parallelizations. And we started to see effort like Alpha, Mesh, TensorFlow, and Zero that come up with very creative ways of combining different forms of parallelizations and different system-level techniques to avoid that the GPU memory, the memory that is available on a single GPU really becomes the main constraint for scaling AI. So that is the trend that we kind of need to be mindful and keep away and keep present. So if you want to play it safe, right, you could basically do some cool yet somewhat boring research, in that sense, safe, right? And what I mean by that is you could still think about communication in deep learning as this kind of reactionary thing that happens, right? I computed my gradients, and that's my event, and it tells me, oh, I now need to communicate it, and then latency matters in that the exposed communication is the one that I want to tackle and reduce. So I can basically spend time and do in network aggregation plus. I can think about congestion control for distributed deep learning, network design, as in communication network design, like the net topology for distributed learning, right? And there's certainly, an opportunity to do very interesting work there. it's also one where certain companies are now increasingly interested, if not also active in that side. Otherwise, right, opposite of that, you can embrace the wild world of deep learning, right? This is the state of machine learning research, as I've come to learn from Twitter. What I mean by that, so if you think about it, right, what's communication, right? Communication in distributed deep learning is a sort of multi-scale spatial and temporal pattern of data transfer, where data basically needs to reach where the compute is at, where the compute is necessitated in that one, right? So you would say, it's really just the workload, stupid. So think about that. And so what we want to do is, in a nutshell, is to really go back at some of the early ideas in this space. And so I refer to kind of like a hidden gem, which was the Boson parameter server paper back from 2015, published in SOCC, where if you actually read the title, there's no deep learning, there's no machine learning, right? But what they were doing at that time, and this is a paper with Eric Shane, they were really showing how important it is to manage the communication in an within essentially a parameter server architecture to get the data where it needs to get at, prioritizing which data transfer should be made, so that overall the computation can progress, but also at the same time without bringing an impact on the accuracy. Okay, but then why stop there? Why do I actually only want to manage the communication that has to happen? I actually want to think about anticipatory computation. What I mean is, I'll get there with some kind of analogies, okay? But the broader mindset is that we want to do systems-aware machine learning, right? We want to bring those opportunities for cross-layer optimization that only really exist if you think carefully about the workload. If you think carefully about what really machine learning is doing. Machine learning is ultimately an optimization problem, and there are some people that or some efforts, right, that we can basically look at as inspiration. So think about Adam, right, which is the optimizer that people typically use. Why do you use Adam instead of SGD? It's because it's a better optimizer. It takes fewer steps to get to where you need. And why? What does it do? It basically has a state. It has an optimizer state. It has essentially a learning rate per parameter of your network, which gets larger, right? It's about optimizing that idea. Or some other work that recently got published in OSDI, Pollux, right? The idea is you don't want to optimize only your system throughput. You actually want to optimize your training throughput. You want to basically be aware that as you vary the batch size, you have implications on how well you're converging. And so you want to, step back and find the correct batch size, so that you jointly optimize your system throughput and the statistical efficiency at which you're converging, right? And so that is, in a sense, what I am proposing to look forward as a more wild opportunity for research, where communications needs to be managed, right? Like it's essentially like the same idea of the step size. Why do I communicate? Why do I have a state for each parameter, right? I need to understand, what do I need to communicate? Which data transfer? What should I prioritize? And so in that regard, I really think that we should be asking the question, can we figure out what is the communications that would maximize my training throughput, rather than just assuming that I need to minimize the latency of everything. So I think that this has higher potential. So I'll invite people to further discuss during this workshop and later on this. And so with that, and perhaps a little bit late, apologies. Thank you all for the attention. If you have to get in touch or you want to get to the papers and so on, those are the links. Thank you.